Hello everyone, my name is Pratik, and in today's tutorial I will show you how you can model vacuum pumps in COMSOL multiphysics softwares. So the modeling of these vacuum pumps becomes very important for the variety of applications like let's say we want to design a vacuum pump for our house, or anyone wants to design some vacuum gripping material, some suction material. For that it becomes important uh, to get the optimized performance of the vacuum pump and our system as well. So we will cover in this lecture we will cover how you can model this in COMSOL, and the system that we would be modeling is the pipe which is shown here. We would be modeling the pipe, and on and this in this pipe on one at one end there is a vacuum pump attached, and we will see that with with what vacuum that you are applying, how what would be the velocity profile that you expect in the pipe, and also the velocity profile and the pressure profile in the pipe, and what will happen if you change the property of the vacuum. So this will be this is all. So we will move on to model this in the COMSOL multiphysics software. So I will just open the software. So when you open the software, this kind of interface pops up. So since the model that I've shown you is in 3D, so we'll click on 3D, and we will go to we have to select the physics now. We'll go to physics, and we have to go to fluid flow, and we have to choose for the laminar flow, because yeah, so the laminar flow physics we have to choose. So yeah, here you see in under the single phase flow, because it's just the air moving, so it's just a single phase flow. So we'll click on the laminar flow and add uh, yeah, study. So the study would be the stationary. Click on stationary, done. And do you want to save changes to the no? So yeah, it will take some time, and so this kind of interface will come. So now first what we have to do is we have to create the geometry for our system. So we have to create so as I've shown you that we are modeling the cylinder, so we have to create the geometry. So currently the length unit is in meters, so usually the pipe is in millimeters, so we'll click millimeters, then right click. So there is a you can directly make cylinder, so just click on cylinder and give it some radius. Let's say we give it radius of 0.25 mm and length of around 10 mm. Click on build all. So you see here, so we have built the pipe. So now we have to define the material in material of this. So what is moving inside? So basically it's the air. So we will choose add material. Just click add material from the library. Here just type here. Let's see what comes. There you see there is a air. You can just click on this. This take automatically takes the properties of the air, so you don't have to mention them separately. And now, so we have made the geometry, we have defined our material, and now we have to define our physics. So is the laminar flow. In the laminar flow, so we in the laminar flow we have to, because it's just we are modeling a small lab scale vacuum pump, which I have shown you in the picture, like this one. So this is small scale. So usually the compressibility for this flow would be income. We have to assume it as an incompressible flow. We don't we are not including any gravity and anything at all now. We have to define the temperature. So temperature we have taken as 293.515 Kelvin, that is like 20 degree Celsius. or we can move it, we can make it around, like, let's say 298 to make it 25 degrees Celsius. We are not using the turbulent model. If you choose here the turbulent, you can use RANS RGD simulation, but I don't want to use as of now. We are considering the flow to be a laminar flow. Just and then this is done. Then we have to give the fluid properties. So fluid properties like density and the dynamic viscosity. So here currently it is shown that you can give them the property here as well, like the density of the air, and you can click on user defined, you can give the density. But currently we will just click from material, so because we have already defined the material here, so this will take the property from the material, and for the viscosity as well it will take the property from there. Then what we have to do is we have to we will click right click on this laminar flow, and under the flow control device you will see there is an option of fan grill vacuum pump. So COMSOL has an inbuilt physics to model the vacuum pump. So just right click on this vacuum pump and choose the surface where you are applying the vacuum. So for our case, we are applying the vacuum at this end. So if you see here, as soon as you click it, there would be a red arrow coming in to just to show the direction of the vacuum. So there's an arrow there. So you have defined the vacuum, and and this edge would be the open edge, basically the inlet for the air. So it's basically we are modeling it like the other end is open to the environment. We will put it the inlet condition. So this choose this inlet condition as this, and give it some pressure, basically let's say 1 atm pressure. We gave it 1 atm pressure, which is static. The total pressure, 1 atmospheric pressure means one, like it's open to the atmosphere. So 1 atm. Suppress, we don't want to suppress backflow. Vacuum pump. Now we have to, so this is the most important thing here. We have to define the property of the vacuum pump that we are using. So usually these properties are specified by the pump that you are using. So basically the industrial grade pump, is it industrial grade pump or the lab scale pump? It comes with the with the with these values, basically. So what would be the static pressure at no flow? You can get it from literature. Even they have the static pressure curves. So usually pumps have a static pressure curves data. So you can click on static curve data, and then you have to provide the value of flux, and at that flux what is the static pressure curve is there. So for my pump, that whatever that I'm using, I got the data from the sheet of the vacuum. So I will just put that data here. I will just copy the data here. Yeah, so I copied the data. The flux is in the, so you have to give the unit here. What is the unit of the flux that you are using? So for my case it is in meter cube per second. So there can be different units based on what unit you have imported your data in. You can choose that. Then for the static pressure curve, chase it is in Pascal for me, so I choose in Pascal. And this the function this is a function, so I'm using it a linear function. And yeah, so that, I guess that is all for the physics part. Then we have defined the vacuum inlet, and this is the wall. Basically this outer covering outer of the pipe will act as a wall. For the wall we have given it currently the no slip condition. So no slip condition. And then I guess physics is defined. Now we will go to on to mesh this. So click on mesh, build all. It will take some time to build the mesh. Yeah, So you see, since you clicked physics controlled mesh, it has chosen the mesh which is best for the physics that you are simulating. So you can see here, so it has created the triangular triangular mesh, and now mesh is there. we'll we will click on the study. On the study, just right click and get initial value for step. So get initial value for a step we do in the model, just to check whether all the things are like we are not committing any blunder, and what kind of results that you will expect. Basically, when you click on this, so you will see that the kind of results that will be coming for the post processing would be velocity and the pressure profile. So yeah, we want to know the pressure inside the pipe and also the velocity, how much velocity is there. So click on stationary and then compute. Let's see whether it runs properly or not. You will see the convergence plots coming. So this first plot shows the percentage error. Second, this also shows error. It's taking some time because the mesh is very fine. So you see the error has reached to the order of 10 to power minus 2, which is good. That means that the physics is properly set for the system and it's converging properly. Now you see here, now you see you got the output for the velocity inside the pipe. So this is this shows, it's plotted in the slice format. So if you see here, it's in slice, and let's say, so this is slice in the YZ plane. Let's make it XY plane. Let's see how it shows. So you see here, so you see, because the conditions that we have used, the velocity in the pipe is coming very high, like 500 meter per second. If we change the condition of the vacuum pump, you will expect lesser velocity. Or if you increase let's say we increase the diameter of the pipe, then also you will get the less velocity. So this shows the velocity profile, and the second one, it shows the pressure profile. So you see where you are applying the pressure, the vacuum, it will show the negative pressure at that end, and at the other end it would be the positive pressure. The negative pressure because we are applying the suction. So that is what we expect. So let's see whether there is some drop in the velocity on the in the pipe. So for that, what we do is, let's plot it. Let's go to results. Go to uh, go to cut line 3D. Just we want to know the velocity at the center, whether what is happening into the velocity between in the center of the pipe. So center would be like it's going in the Z direction. So from 0 to 10, it's going from 0 to 10 in the Z direction. So define 0 to 10. This would be 0, I guess, dot. So if you see, yeah, see. So this is a line which is plotted here, and we want to know the velocity along this line. So we have defined the cut line here. Now go to results, go to 1D plot group, and in the 1D plot group, we choose the line graph. So line graph, we have to data set, we have to use the cut line 3D, because that is the cut line that we defined just now. And the thing that we want to plot is the velocity. Click on OK. So you see here. So the velocity is around 532, which is like maximum where there is a pipe, like where there is a vacuum, where we are applying vacuum, which is what we expect. But with the length, the there is there is a decrease in the velocity. Basically, there could be a velocity loss along the length of the pipe, which is what we expect. And at after 10 millimeter, the velocity reaches to somewhere around 504 meter per seconds. So yeah, so that's how you can model the vacuum pump in COMSOL multiphysics. Uh, I can also show you with the different fluxes and different pump size and different diameters, but I guess you guys can do that by your own. But if you have any, you can try it or on your own. But if you have any questions, you can just mail me or comment on the video, and I will try to solve the problem. So yeah, I guess that is all for this video. Thank you.